Good morning, cadets. Now we are going to learn a very important device, that is potentiometer. Potentiometer is a device which is usually used to compare EMFs of two cells. Since no involvement of current being there by using a potentiometer, the potentiometer doesn't draw the current from the cell. The potentiometer can also be used to measure the potential difference, EMF of a cell, and it is also used to find the internal resistance of a primary cell. So potentiometer is a device which is used to measure potential difference across two endpoints of a current carrying conductor, or it is also used to find the EMF of a cell, and it is also used to find the internal resistance of a primary cell. Potentiometer is also used to compare EMF of two primary cells. Since it does not draw any current from such cells, the measurement of potential difference or the measurement of the EMF using potentiometer is of more accuracy than compared to the usual voltmeter. How is it? We are going to study now. Right? The potentiometer consists of a very long uniform wire, a very long constantan or manganese wire which is of uniform cross section. It may be of 4 meter length or 6 meter length. So let me take a potentiometer having 4 meter length wire. If you take a 4 meter length wire and stretch it, it's going to be a very long from this end to this end. Then it becomes inconvenient. It becomes difficult for doing the experiments, for the measurements. Right? Therefore, this 4 meter wire is cut into 4 segments, each of 1 meter. 4 segments with each segment of 1 meter. And they are joined end to end with the help of thick metal strips. Suppose this is a 1 meter wire. So it will be having such 4 segments, so that the total length of the wire becomes 4 meter, and they will be joined here end to end, side by side. If it is joined here, next it will be joined here side by side with the help of thick metal strips. These are metal strips. And this end, if you take it as P, the other end is taken as Q, right? So the total length of this wire in this potentiometer is of 4 meter, 0 to 100 centimeter, 100 to 200 centimeter, 200 to 300 centimeter, 300 to 400 centimeter, that is 4 meter wire. Okay. Now, these metal strips are being thick, they will provide negligible resistance. Thick metal strips will have very less resistance, almost zero resistance, you can say minimum resistance. Therefore, they do not offer any resistance. Therefore, almost this end is taken as this. So 0 to 100, 100 to 200, 200 to 300, 300 to 400. Okay. And this will be provided with a meter stick. Just below this, it will be provided with the meter stick. So one can measure the length of the wire at any point. Okay. First of all, we will understand the principle of potentiometer. Principle of potentiometer. Here, when we allow constant current in this long wire, then from point to point, if you go on measuring the potential difference, the potential difference value goes on changing. The potential difference goes on changing. The reason is, as length of the wire increases, the resistance of the wire increases. We know this property. The resistance of a wire is directly proportional to its length. Therefore, as length of the wire increases, means this wire is going to have constant current. As length of the current carrying wire increases, the resistance of the wire increases. So, resistance is being directly proportional to L. When the current is constant, then we can say potential difference is directly proportional to length of the wire. So, this is actually connected to a battery. Here, this is connected to a battery which drives constant current. This battery is driving constant current, therefore it is called as driving battery. Another name is auxiliary battery. Another name is auxiliary battery, means main battery. And this is connected with the variable resistance. Variable resistance. And here it's taken with a key. One key. Let us call this key as K1. Right? When we close the key, what happens? See here, this is positive terminal and this is negative terminal of the battery. By varying this resistance, usually it is a rheostat. Symbolically, it is written rheostat, or you can also call it as variable resistor. Right? When we change this resistance, the current flowing through this wire changes. For a one particular value, we choose, let us say 1 ampere of current. We choose 1 ampere of current using a ammeter here. Ammeter is not shown. Using an ammeter, we maintain constant current. Right? And here, it will be connected with a voltmeter in order to measure the voltages. See here, as you move from one end to another end, the length of the wire increases, as I said. As length increases, resistance increases. So, we say that voltage across any two points, across any two end points of a current carrying conductor is directly proportional to its length. This is the principle of potentiometer. So, I will write here, for a conductor carrying current, the potential difference between 2 points if we write it as V, is a function of L. It is a function of L. As L increases, potential difference increases. It is found to be directly proportional to the length. If we take 50 centimeter, it will have one value of potential difference. If you take 100 centimeter, potential difference increases. So, the potential drop increases as length increases. Right? Suppose we have connected a 6-volt battery here. Without, let us think that this 6-volt battery has negligible internal resistance. 6-volt battery having negligible internal resistance. So, to this 6-volt battery, we have connected an external resistor whose length is of 4 meter. Some potentiometers may be having 6 meter length also. It will be having 6 segments of such type, which are joined side by side with the help of thick metal strips. It may be having 6 segments. then its total length is 6 meter, right? In this example, we have taken a potentiometer having 4 segments, so that total length is 4 meter. So, for this entire PQ external resistance, you see the potential between the two ends of this wire is directly proportional to, potential difference is directly proportional to length of that wire. Reason is, for constant current carrying conductor, for a conductor or a wire having constant current, now it is having constant current. Current is not being changed. Then what are the variables? V and R. Using the Ohm's law, V is equal to Ri. When I is constant, you can see, when I is constant, then V is directly proportional to R. But we know R is directly proportional to L, because it's a uniform wire having same thickness throughout from 0 end to 4 meter end. From 0 centimeter to 400 centimeter, the thickness of the wire is same, uniform cross section. Therefore, resistance of the wire is directly proportional to L, and it is of the same wire, say either constant or manganese, its resistivity is also remaining same. So, V is directly proportional to R, and R is directly proportional to length. Therefore, since we do not know the value of R, we can say V is, so we can conclude that V is directly proportional to length. This is the principle of potentiometer. Now, if you take out this proportionality sign, then V is equal to one constant times L, where that constant phi is called potential gradient. Potential gradient. So, potential gradient is measured as potential drop per unit centimeter. Potential drop per unit length. Per unit length is called as potential gradient. So, it is measured usually it is measured voltage per meter. That is the SI unit. Voltage per meter is the SI unit. But here, practically, it is measured as voltage per centimeter. Usually, it is measured in voltage per centimeter. P per centimeter, volts per centimeter. Okay. So, this is the principle of the potentiometer. Now, first we will learn about the how potentiometer is used to compare the EMFs of two given primary cells. We use primary cells, right? The primary cells like Leclanche cell, dry cell, or we can use another one, Leclanche cell, another one, Daniell cell. So, using these two, one can compare the EMFs of these two cells using this potentiometer. So, we will learn comparison of EMFs of two given primary cells. So, now we will learn to compare the EMFs of two given primary cells like Daniell cell and Leclanche cell, right? So, this is the circuit. So, before we connect, the key is open. Now, it is in open circuit, right? Now, to this point P, which is a 0 end, two cells whose EMFs are to be compared are connected. Suppose this is cell of EMF E1, maybe let us say Leclanche cell, and the another cell of EMF E2, they are connected parallel like this. Both the positive terminals, you can see both the positive terminals are connected to this point P, and you can see even the positive terminal of the auxiliary battery is also connected to the same point P. So, all the positive terminals are connected to point P. Now, these negative terminals are now left free. Now, these negative terminals are connected to a key called as two-way key. Here it is represented by a box. It is called two-way key. So I will take this point as 1, this point as 2, and the middle point as 3. Between 1 and 3, if you close the key, right, then the cell of EMF E1 will be in circuit. If you take out this key and close it here between 2 and 3, then cell of EMF E2 will be in connection, right. Now this middle term, common terminal, is connected to a galvanometer, right, and the other terminal of the galvanometer is connected to a jockey, a sliding contact jockey, right, which will be having a very long wire. So that sliding contact is free and it can be slided on this wire from 0 to 100, 100 to 150, 160 and so on up to 200, 250 to 300 and so on. It is left free so that you can go on sliding it and try for getting the balancing length, right. What is that balancing length? Let us see. Now this is the other end. The other end is connected with a jockey, right. So here the loops represent, they are not connected here, and the free end is connected to a jockey G, where J is for sliding contact. J here means sliding contact called as jockey, metallic sliding contact. Okay, to start with, we close the key K1. Key K1 is closed, and in the two-way key, you can see here, these are the two negative terminals of the cells E1 and E2. In the two-way key, first the gaps between 1 and 3 are closed, and in a two-way key, 1 and 3 are closed, so that cell E1 is in the circuit. Cell E1 is in the circuit. Now look at this. The current flows like this. This is the current maintained by the auxiliary battery, and thus the circuit is completed. Some constant value of current is chosen and it will be kept constant using the rheostat and this auxiliary battery. Remember, what is the meaning of auxiliary battery? Auxiliary battery is the main battery which provides constant current in the 4 meter length of the wire or 6 meter length of the potentiometer wire. It is also called as driving cell or driver cell, which is used to maintain constant current. And remember, the EMF of this driver cell or auxiliary battery must be higher than the EMFs of these two cells, right? Must be higher than the EMFs of these two cells, maybe like 4.5 volt or 6 volt, so that the voltage will be very much higher compared to the EMFs of these primary cells. They will be hardly 1.5 or 1.1 volt. Okay. So this is to be kept in mind. Okay. When constant current is maintained. Now this sliding contact, when the two-way key is closed here, when this two-way key is closed between 1 and 3, this sliding contact is taken over this wire, slided over this wire along this length of the wire until the galvanometer reads 0 deflection. Slide the contact jockey along the wire until the galvanometer reads deflection. Suppose the galvanometer reads deflection at point D. When it reads 0 deflection at point D, we have to measure this length 100 plus let us say 155 centimeter. So 100 plus 110, 20, 30, 40, 50, 55 centimeter. Like this we have to measure the length. And what happens at this point to make this galvanometer 0? The reason is the galvanometer reads to 0 at this particular length. At that moment, the potential difference between PD, between P to D of this length of the wire, potential difference is exactly equal to the EMF of this cell, right? So, whatever the potential difference, if it is 0, then if the potential difference becomes exactly equal to 0, then what happens? No current flows through this circuit. No current flows through this circuit. The current is not drawn from this cell at all when the galvanometer reads 0 deflection. This is the importance of the potentiometer. Without taking or without drawing the current from the cell, it is capable of measuring the EMF, and it is capable of measuring the voltage, and it is capable of comparing the EMFs of two cells, right? Now, when we slide, what happens? When jockey is slided, let D be the point at which galvanometer reads 0. Galvanometer reads 0 means the current through the galvanometer is 0. Then what happens? If you apply even Kirchhoff's law to this closed circuit now, P, E1, 3, G, D, P. If you apply Kirchhoff's law, Kirchhoff's voltage law to this loop P, E1, 3, G, D, P, applying KVL to the loop P, E1, 3, PE1 1 3, okay, PE1 you can say PE1 1, PE1 1 which is connected with 3, PE1 1, G, D, back to P. So this is a closed circuit. When you apply it to this loop, then what do you find out? EMF provided by this loop is E1. E1, and the potential difference between P and D is given by phi L1. It is given by phi L1. So, E minus phi L1 is equal to 0. Sum of the potential drops is equal to 0. This is according to Kirchhoff's voltage rule, and this is being taken according to the circuit. So, you can take either phi L1 minus E equal to 0, E here is E1, right? Phi L1 minus E equal to 0. So, that implies E1 is equal to phi L1. Or using the principle of the potentiometer itself, we know that the potential difference across the two ends of this particular potentiometer wire is directly proportional to the EMF. EMF here is E1. So, E1 is directly proportional to L1. So, directly we can write E1 is therefore equal to phi L1. Directly also one can write without applying Kirchhoff's voltage law. So, this is the case for the cell of EMF E1, when cell of EMF E1 is connected. Now, after measuring this length L1 is noted down. L1 for balancing length, where L1 is the balancing length. L1 is the balancing length for which galvanometer reads 0 deflection. Now, in the same way, this key is now taken out and closed This key is now taken out and closed between the gap of 2 and 3. Key K2 is now closed between the gap 2 and 3, between the gaps 2 and 3, between the gap 2 and 3, right? Now E2 is in circuit. E2 is in circuit. When E2 is in circuit, directly I can write E2 is directly proportional to phi. E2 is directly proportional to L2. So this implies E2 is equal to phi L2, where L2 is another balancing length. Means now the same procedure is repeated. Again, the jockey is now slided like this at one particular length, let us say about 80 centimeter, let us say about 85 centimeter, the jockey is like, right? Now let us say this is D dash. Now this is of length L2 and earlier length was L1. For this length L2, say about 85 centimeter, the galvanometer reads 0 deflection. So L2 is the balancing length. L2 is balancing length for cell E2. Now we got two equations. E1 is equal to phi L1, E2 equal to phi L2. So E1 by E2 equal to phi cancels. Therefore, E1 by E2, if you take it, phi cancels, you are getting L1 by L2. E1 by E2 is equal to L1 by L2. That's how we compare the EMFs of two cells. Thus, you can see here, by just taking the ratio E1 is equal to phi L1, E2 equal to phi L2, E1 by E2 gives us L1 by L2. Just by noting down the corresponding balancing lengths of these particular primary cells L1 and L2, one can compare the EMFs of given two cells. Now out of these two cells, if there is one standard cell whose EMF is already known, suppose we know the EMF of E2, suppose we know the EMF of E2. Let us say E2 is a dry cell. We know EMF of a dry cell. It is 1.5 volts. Dry cell means the cell which is used in our torch, right? Or in your remote, the cell that is used in your remote. If it is used here instead of another primary cell like any chemical cell, any electrolytic cell. If we use a dry cell, then we know already the value of E2. Then we can find out the EMF of E1. If E2 is a standard cell of known value, then E1 can be calculated as, then E1 is equal to E2 into bracket L1 by L2. So that's how we calculate EMF, unknown EMF of a cell. That's how we calculate unknown EMF of a cell. The very important thing here is when we adjust it for balancing length, for which the galvanometer reads 0 deflection, no current flows through this circuit. No current flows through this circuit. It means without drawing any current from these cells, it is capable of measuring its EMF. That is the advantage of the potentiometer. So potentiometer reads more accurately, its accuracy is more than the accuracy of the voltmeter. What actually voltmeter does? Voltmeter draws some amount of current from the source. If you connect across the two ends of this cell, the two terminals of a voltmeter reads voltage. But what it does? Actually it takes some current from this cell and measures. By drawing some current from the cell, it measures. Therefore, the voltage measured by voltmeter will be slightly less than the actual voltage measured by the potentiometer. This is the advantage of potentiometer, right? without drawing any current from the source, it can measure its voltage or it can measure its potential difference or EMF. Okay, this is one experiment which we are going to do in our laboratory, that is comparison of EMFs of two cells. The next one is one more, to find the internal resistance of a given primary cell. To find the internal resistance of a given primary cell. So now the second experiment is to find the internal resistance of a given primary cell. So only one cell is taken here and it is connected to the point P. The positive terminal of that cell is connected to the point P, and to this negative terminal a resistance box of usually low resistance is connected in parallel. And here there is a key K2 being taken. Key K2 is being taken and remaining circuit is as usual. Instead of cell E2, there is a resistance box of some resistance, known resistance, which can be taken from here. So this is a cell of EMF E, let us say having some internal resistance, symbolically shown as R is taken. There is no much difference in the circuit. Okay. Now here again it is connected to galvanometer here. The galvanometer, other end of the galvanometer is connected to a jockey, right? Now to start with the experiment, again we close the key K1 and a current flows through this 4-meter wire of the potentiometer and some constant value of current is chosen. Next, without closing key K2, K2 is kept open first. Close key K1 and keep K2 open. Keep K2 open means only the upper circuit is in contact now. That is cell consisting of circuit consisting of cell of EMF is in contact, is in the circuit. Then go on sliding on this wire. At one particular point D, it shows null deflection. It shows zero deflection. And note down that point, note down that length as, let us say, L1. Go on sliding along the length of the wire. At one particular point D, the galvanometer reads zero deflection and measure that balancing length. Let us say it is 100 and something as we have measured earlier. Let us take that length as L1. So keep K1 closed and K2 open. Then let L2 be the balancing length. L2 be the balancing length. Then EMF E of this is equal to phi L1 as we have done earlier, because E is directly proportional to L1. E is directly proportional to L1 implies E is equal to phi L1, right? So this is keeping K2 open. Next, we take out this sliding contact and close this key K2. After closing this key K2, we take some convenient resistance R from the resistance box. Let us say 5 ohm or 10 ohm. Some suitable resistance is taken out which is connected in parallel with this. So that now the current will be flowing not only through this cell, it will be flowing through this resistance which is connected in parallel with the cell. As a result, it will give you a potential difference which is now called as terminal potential difference. And again, go on sliding the jockey, sliding contact along the length of the wire. At one particular length, say L2, the galvanometer reads zero deflection again. Now, close K2 and go on sliding the sliding contact, that is jockey. Let L2 be the balancing length. L2 be the balancing length. Now for this L2, it is no more going to be E now, it is going to be potential difference, terminal potential difference. Therefore, L2 be the balancing length for some known resistance R. When resistance R, low value, usually 5 ohm or 10 ohm, within that value itself the value will be taken out when resistance R is chosen in the path. Next, now then the terminal potential difference. Terminal potential difference V is directly proportional to L2 now, where L2 is the balancing length which is measured from P to D dash. So V is therefore equal to phi L2. This phi is constant. Volt per centimeter, that is potential drop per centimeter, is always constant. Therefore, we can very easily write E equal to phi L1, V equal to phi L2. Now taking the ratio of these, we get E by V equal to phi getting cancelled, L1 by L2. But now we need to find out the internal resistance of the cell. Make use of the equations that we have already learnt. We know that V is equal to Ri, potential difference across the resistance is equal to Ri, and we also know that terminal potential difference is given by V equal to E minus I small r, where small r is the internal resistance. So if you substitute here, we get Ri equal to E minus IR. So I can find out what is the value of E. Therefore, E is equal to R into bracket, R plus R. If you take this IR this side, it becomes positive, R plus R into I. So this is the equation for E, and now you see the equation for V. So substitute these values. This is 2, this is 1. Substituting 1 and 2 in this main equation E by V, we get the result for internal resistance R. You can see now after substitution, E by V is equal to L1 by L2. So if we substitute the value of E is substituted as R plus R into I, and V is terminal potential difference substituted as Ri. I cancels. When I cancels, we get R plus R divided by R is equal to L1 by L2. We want to find out internal resistance. So if you split this, we get R upon R plus 1 is equal to L1 by L2. Therefore, R by R is equal to L1 by L2 minus 1. So we want the internal resistance. Therefore, internal resistance R is equal to, you can see here, R, capital R into bracket, L1 by L2 minus 1. So this is how, using this equation, we find out the internal resistance of a cell. You can take it as R into bracket L1 minus L2 by L1 by L2, L1 minus L2 by L2. This gives us the internal resistance of a cell, right? So this R value is a known value, that is either 5 ohm or 10 ohm, whatever it is. So L1 is the balancing length without taking the resistance R, and L2 is the balancing length after taking the resistance R. Then we get the internal resistance, right? This procedure is repeated for different values of the known resistance R. We will get different values of L2, and thus we will be able to get internal resistance. So one can take average value of internal resistance. In this way, we do two experiments in our laboratory using this potentiometer. First is to compare the EMF of two given primary cells. Second one is to find the internal resistance of a primary cell. Okay. We will solve numerical problems based on this in the next video. Thank you. Have a nice day. Bye.